Okay, so enough about myself and then exploratory. Now let's get into today's content, which is a linear regression. So linear regression is kind of like beside belong to the analytics box in this data science workflow. So to do, I want to start with the data. So data we're going to use is this employee data. So one row is one employee, and then there are various informations that's such as gender or job role or how many years this given employee is working for this company, and then how much this company is making, the monthly income. So let's say that we are interested in this monthly income. So what are the questions we start with? So typical questions can be like, what is monthly income in this company? And average monthly income, it turned out 6,503, which you can find by using a summary view, for example, in Exploratory. So now that question kind of gives you some kind of like information about the monthly income in this company, but is that a good question? So, so here's a quote from John Tukey, who is the one who basically created this field called exploratory data science. But his quote is far better an approximate answer to the right question, which is often vague, than an exact answer to the wrong question, which can always be made precise. So we have to kind of figure out what are the questions we should ask in order to understand the monthly income better for this company. So it's always, there's a guideline, there's a guideline for you to do like exploratory data analysis. The two key questions is always around these two. So the variance and covariate or correlation. I'm going to use correlation as the word here to make it more easier for any background folks to understand. But these are the two things, what that means. So the variance, let's start with the variance. I know this is like actually linear regression seminar, but let me just kind of get to this variance and correlation, then get into how the linear regression model works. Anyway, so we answer the question of like what is the average of monthly income, which is $6,503. But the truth is that the data varies, right? So like that's starting from maybe like 1,000 people who is making 1,000 for monthly income to 20,000. And then when you open up the box, and then like there are different, like many people actually turned out like making less than 6,000. And then so there's certain people, maybe like a few number of the people making greater than 6,000, but the value can be super big, like 20,000 or something like that. So the variance is really about like how the data like varies, right? Like from the, let's say like average, maybe like this data in this particular case, maybe like there are $2,000 difference. And so on. So data varies. And then like, in order for us to understand this monthly income, it's important to understand like how the monthly income is valued, or the variance for the monthly income. And then once we understand that like the monthly income is not a single number, there's a bunch of different types of numbers, then the question is what makes monthly income change and how? And that's where like we get this thing called correlation. And the correlation is a relationship where changes in one variable happen together with changes in another variable with a certain rule. And then typically, like I'm sure like you have seen this type of the chart. So like when you have the scatter chart, and then like X and Y, and X can be, for example, age, and Y can be monthly income. And then there are different types of relationships, right? So from left to right, left is a strong negative correlation, which means like one value increase on the x-axis tend to happen together with like a certain value decrease on the y-axis. And the opposite end on the right-hand side, which is a strong positive correlation, and that means like one value increase on the x-axis tend to happen together with the certain value increase on the y-axis. So increase and increase. And then at the center, it says no correlation, and the number says 0. That means there's no correlation. So whatever the value change in the x-axis, have no sort of like effect or like nothing to do with the changes on the y-axis. They don't affect each other at all. And then like we typically use this number, the correlation number is usually start from like the smallest is a -1 and the strongest, the biggest is 1. So -1 is a strong negative and a 1 is a strong positive, and then the between, which is 0, is a no correlation. So this concept becomes more important later, like when I start getting to the linear regression. Okay, so so once now, like we kind of know or like understand the correlation. So like why correlation is important? Well, so when you basically the correlation is almost like one of the most important concepts in data science or data analysis, precisely. So, like I said, the data values, so, right? So, like when we said, like for example, monthly income or like the number of the customers or conversion rate, whatever that is, there's always there's a variance, and then the variance is basically is a problem because I mean it's a challenge because when you simply ask, say, like how much is the income that would be in this company, like when you join this company, how much is your monthly income? Then you can't really answer because data varies. So giving you the answer of the average is not really going to help you. So that is called uncertainty, right? So between 1,000, 20,000, so there's that much difference, and that's the uncertainty. But if we can find a correlation between monthly income and working years, for example, it turned out like the working years and monthly income was strongly correlated, like this chart. Then we can answer what it said, like, hey, you know what, like this person is working for about 20 years. That means we can kind of estimate, we can estimate approximation of the monthly income. And let's say like about like 15,000 or something. Might not be perfect, precise answer, but can estimate around $15,000 or something. So, which means basically the correlation can reduce the uncertainty of variance along with the variance by finding a correlation, and then like we can kind of get to the something what we want to know. So if we can find strong correlation, that makes it easier to explain how monthly income changes. And also that means we can predict what monthly income will be. So that's why the correlation is important. And then but here's one note. I'm sure like you have heard about this before, and maybe many times the correlation is not equal to causation. Causation is a special type of correlation. But if we can confirm a given correlation, let's say that you find a correlation, and if you confirm or you can test that correlation, and then confirm that that is actually the causation, then we can control the outcome, like by manipulating or by influencing the variable, and then like we can get the certain result. But we're not going to that type of the causation this time, but we're going to focus purely on the correlation. So the correlation in the exploratory or in any word, like you can get the easiest way to find the correlation is to run the correlation algorithm, and then. So let's take a look at that here quickly. So here is the employee data, the one like I was showing in the slides. And then like basically like what we want to know is this like how this monthly income gets decided, or like how this change, right? So we want to know what are the other variables that are highly correlated. Then like we can have better understanding about this monthly income. So first thing I want to do is, let's say I go into the analytics view, and then there's a correlation by columns, and then there's a variable column. Here we can select all the numerical variables. We can't select the categorical, but we can select all the numerical variables. And then we can quickly run it, and then you get this type of view. And then let's see, like, what are the variables that are correlated to monthly income, right? Like a highly correlated. So either like a strongly positively correlated is like a red color, and then like a strongly negatively correlated, it could be like blue color. So here's a monthly color, monthly income. And then here there's a job level. And then there's another one, it's called total working years. So it looks like these two are highly correlated. And what that means, so like when you go to the chart and then like we can use this numerical and numerical, like we can use the scatter plot to see how they're related or their relationship. So I'm going to select the scatter plot. And then first one, the job level, and then against the monthly income. And let's see like how that is correlated. And then like, it looks like here's a job level. It looks like 1, 2, 3, 4, 5. These are 5 levels. And then like, as the job level increased and the monthly income seems to go up. And an easier way to see this type of relationship is to draw a trend line. And then it says linear regression. And that's exactly the topic that we're going to cover today. But at this point, like I want to show you like how these two variables between job level and monthly income are correlated. And when you move the mouse on top of the line, like you can see the correlation. Here it says 0.95. So it's very highly correlated based on this number. So now, and the other variables here, or like metrics here, p-value, r-square, coefficient. Those are the 3 things I'm gonna talk about in a minute. So now another one is called total working years. So let's select that too. And then so now the x-axis is total working years and y-axis monthly income. And this is also sort of like a correlated. So here I see correlation is 0.77. So less correlated compared to the job level, but still nonetheless, it's basically what it's saying here is sort of like when you work longer in this company, and then like you get higher monthly income. So that's really the correlation. Okay, so now is finding correlation enough? So like once we understand it, like 0.77, 0.20, so at the end of the day, so what's that going to help me to getting more insights to answer the question in terms of like understanding what the monthly incomes and how the monthly incomes get decided. So these are 3 questions. So first one, so now that we know that some correlations between those variables, now how big is that correlation? And then what I mean by big is that strong enough that we should really pay attention to it? We should really go kind of dig into it. I mean, in this case, we have like a few correlation. Are they equally important? And that's the question we want to answer. Second question is how much of the variance can it explain? If there's a correlation, but does that mean that's the when the monthly income change, is that like exact change that this variable for like total working years or job level can explain? Likely so, it's not like a single straight line. It's not like a correlation of 1. There's like a 0.77 or 0.9, 0.9 or something. So might have some kind of correlation, but might not be able to explain all the changes in the monthly income. So we want to understand how much of the variance can it explain, can a given variable explain. And then the third question is how much of the change in monthly income we can expect by a change in working years, for example. So for example, total working years, let's say like when you increase 1 year, when you have 5 years, when you have 20 years, how much of that change, increase or decrease you can expect in the monthly income. So those are the 3 questions that like, we want to answer. And that's where the linear regression model come in. So, so to get to the linear regression regression, let's understand the basics first. So what the linear regression? The linear regression is, I'm going to explain, but the why I'm talking about this linear regression is it's an old and basic regression algorithms. But due to its simplicity, it is still one of the most commonly used statistical or machine learning algorithm in the data science field. I bracketed it or machine, so like it's up to you. Like it's not a big deal, but usually like people say like this type of algorithm is statistical learning algorithm because it's coming from kind of like a background of it's more like a statistical side of things rather than like engineering side of things. Usually when I said a statistical learning algorithm, and the model in the statistical learning algorithm usually is a formula. It's like kind of a mathematical formula where machine learning algorithms tend to be not necessarily expressed by the formula, more rather it's more like if-else condition kind of things. So, but that difference is not really important at this moment. So let's get into what the linear regression is. So let's imagine like we have like 5 employees, and then like their working years, the monthly income, and based on the information, like we place them on the 2-dimensional scatter plot of them. And then we can draw the line, and then like go through all these employees. And then we can express this line by this one simple formula, like monthly income equal 500 multiply working years plus 5,000. And then this is probably it's kind of like a simple enough formula. So like then we can say like, hey, how many working years? Let's say like one more year you work in this company, then like you multiply 500, so like that's like a 500. So then like you can get the monthly income, like how much you monthly income get. So, but in reality, the data never be on a straight line. Like there's always like there's a variance. So, maybe like something like this. And then, so the line is not, if we try to draw the line to cover all these 5, and then like it gets kind of a zigzag. But that's not what we want here. We want to find a simple pattern that can explain both the given data and also the data we don't have at hand. And then like we want to see the kind of like a sort of like overall trend. To do, like one of the things we can do is to draw a line, to straight line, to make the distance between the actual values and the line to be minimum. So the difference here is that you can see the red dotted lines, and we want to make these red dotted lines to be minimum. And then I can find the perfect spot, and then I can draw the blue line. And then this blue line can be expressed as this formula, like monthly income equal 500 multiplied working years plus 5,000. And this blue line is the linear regression model. In other words, this formula that above is the model that expresses this blue line. Okay, and then this 500 part is a slope, and then this 5,000 part is something called y-intercept. That means when the x value is 0, what is the value on that y-axis? And the linear regression algorithm finds these 2 parameters based on the given data and build a model. Sometimes we call it a prediction model. So the parameters we are talking about here is 500 and 5,000. And in this case is a slope and an intercept. And in the slope, I want to actually talk about a little bit more here. The slope here is happen to be 500. So that means 1 year increase in working years will increase monthly income for like $500. So that's really what the slope is. And it can be steeper. Let's say that we increase 1,000. That means 1 year increase in working years will increase monthly income for $1,000. It can go opposite. It can go negative too. So like let's say like if the slope is minus 500, that means 1 year increase in working years will decrease monthly income for $500. Definitely not the kind of company you want to work for. But that's beside the point. And then this slope can be 0. And then when it's zero, what that means is that like regardless of the values in working years, so like no matter how many years you work, like your monthly income is always 5,000. This is a typo. It's actually at the above it says 5,000, but that should have been 5,500. But it's always $5,500. So that's zero. So this slope zero means it's actually we can say like working years and monthly income are independent. They don't have any effect on each other. So the values in both variables can be varied, but they don't go in the same way, or they don't have any relationship in terms of the direction or amount of the change or anything like that. So they independently change. Okay, so that is zero. And this concept is called independent. So monthly income and working years are independent, and that means no effect on the other side. And this concept becomes important later. So I just want to point out here. Okay, and then one thing before getting into more detail. So like explain and predict. So when you build this kind of model, right? Like we call it prediction model sometimes, or just a simple model. What we try to do is two things. So like one is explaining, and then also the predict. And then these two concepts sometimes get kind of mashed to each other, and because it looks like very similar things. So I want to just clarify one thing here. So we have this model, right? Like monthly income equal 500 multiplied working years, blah blah blah. So explaining is like basically like 1 year increase in working years would increase monthly income for $500. And I just explained like the sort of phenomena around monthly income in this company, right? But a predict is, let's say like if you are working about like 15 years in this company, and then like what is the monthly income you will expect to get, right? So, and then you get the values. And then that's you're really predicting. So there, sort of like explains basically the logic, and the predict is of course like what is going to happen in the future. It doesn't have to be in the future, but like if you're given value, and then like what is the value that you're going to get. So that's the predict. And then it's not that big deal at this point, but we want to I'm going to focus on more like explainability rather than predictability in this seminar. So anyway, now having that, if we clear that away, so that we are so far like I've been talking about this something particularly called simple linear regression, which means the target value or like the something, let's say like monthly income. And we are trying to understand the monthly income based on only one variable, in this case, working years. And then as opposed to that, once you start adding more variables, because in this world, I mean, there's nothing's that simple, right? So that even this monthly income, it's hard to believe like only working years is the only things that like drives the changes in monthly income. Usually you have other things, maybe the talent, maybe the efficiency or the productivity, or maybe like a type of the job you do. So typically like you throw more variables and then explain as the sort of like additive, as the result of the additive, then like you can explain how the monthly income change. So here, for example, like working years and a job level. And then so you have like a two or more, and we call multiple linear regression. In today's session though, like I'm gonna just focus on simple linear regression first to get that to understand what the linear regression model can do first. And then in the next seminar, which is next week, I'm gonna get into the multiple linear regression, because it requires a little bit more sort of interpretation of like any what's happening inside the model. Okay, so and also like another thing is this concept that like I want to mention, point out, which is called residuals. Because in the real world, so nothing can be on the straight line, right? So like always there's some differences between, I mean, like we can't express what's happening in the world or even the company or whatever by drawing this kind of simple line. So so there's always a difference between the actual data and this sort of like the estimated data by this model. In this case, that is blue line. And that is called residuals. And then basically, in order to evaluate how this model is, or how good this model is, or how bad this model is, we actually use this information, like how much the difference between the actual value and the estimated values produced by the model. Okay. So let's actually do it first, and then like, I'm gonna get into some of the concept as well. So now that we know the correlation, so we want to actually start building the linear regression model. So to do in Exploratory, go to the analytics view, and then there's a linear regression analysis. And then here, the target variable is we want to know the monthly income. And the predictor variable, you can select multiple, but like I said, like today, I want to focus on just a simple linear regression. So like I'm going to pick just one. And then let's start with this like a total working years, and click OK, and then run. And then we get this view. This is like a coefficient under the coefficients tab. And then like when you move the mouse around the dot, and you can see like a bunch of information here, like a p-value, and also in the middle, there's a coefficient. It says 467. And this information is a visualized result of the information you see here in the coefficient table. And you see the total working years, and then that coefficient 467 is coming from this column. And then there's a standard error and a t-ratio, p-value, and a confidence high and low, and other information as well. But for now, let's start with this coefficient. Okay, so so what this coefficient really is that that is a slope. Okay, so now by using this coefficient information here, we can basically write down that formula to calculate the monthly income, to estimate the monthly income based on the total working years. And then the formula can be like this. Okay, so now let's understand this thing a little bit more here. So this time we get 467, or about 468. And that means, oops, there's a Japanese translation there. Sorry about that. But the slope is 468, and that means 1 year increase in the working years at $468 for the monthly income. Okay, and then now this is kind of like easy or simple, I hope, because, or relatively simple, I should say, because a monthly income is a numeric, right? Like, so linear regression, by the way, is they always estimate the numerical outcome or numerical variables. So based on the variable, in this case, the working years, which is a numeric data type. So, and essentially, like we already generated the scatter plot chart, right? Like, so based on the numeric, and then I can estimate the numerical variable. But now, sometimes things get a little bit more complicated. That is when we have a categorical variable as a predictor. So what that means? When you have the categorical on the x-axis, for example, and in this case, let's pick department, right? So in this data, so the sales department, research and development, R&D, and then the human resource, HR. And then each department have the different variations of monthly income. And then we want to understand these two variables have any sort of like a relationship, or more like a correlation kind of relationship. right? So that when you change the department, maybe like you expect the monthly income to go higher or lower. And then we can actually do it here as well. And so let's just try to do it. So here the predictor variable, and instead of selecting total working years, I'm going to select the department for now, and then click the run button here. And then like let's go to the coefficient tab, and then like I see like a department sales and a department human resource. And this can be a little weird because we had only one variable now, but now we see two variables. But also we see like sales and then human resource. What happened to the R&D? Because this variable like or column department has three values, but now like we see only two. So that's what I want to take some time to explain here. Okay, so when you get the categorical variable, in order for you to understand the coefficient becomes slightly different from when you have numerical variable as a predictor. And then when you, in order to interpret the coefficient for the categorical variable, you always need to compare to the base level. So what is the base level? Base level is in R or exploratory, there's a data type called factors, and you can basically set the order of the values of the categorical columns or variable. So in this case, or in exploratory, like we set the base level by using the most frequent value in a column or in a variable. So in this case, research and development, so the more employee in this company are in the research and development or R&D, so we have more people than the sales and HR. So that's why this happen to become the base level. You can change it if you like, but for now, let's keep it as go with the default. And then you can always check like what is this the base level. You can go to the summary view or coefficient view, coefficient table view to see what is the base level of a given variable. So in this case, R&D is the base level. So that, and then what's happening is as part of the model building behind the scene, in this case, it's actually the R. I mean, like linear regression, the algorithm, convert the data into kind of like a wide format, which means the categorical column, in this case, the department, the values of that becomes the column. So in this case, in the sales column, the HR column. And then once we have that, then like each employee, let's say like if this case, Peter is belong to sales department, and then Peter will have 1 for sales, but 0 for the HR. So now like we can express which department each employee belong to as by using the numbers, either 1 or 0. And then that's very important because this linear regression model is a statistical model or mathematical model. So like you gotta express the data by using a formula. And then when you have the mathematical formula, you can't have like a characters or letters and stuff, right? So, but by doing this kind of transformation, then we can even express the department or the categorical information in the mathematical formula. So that's what is happening here. One tricky thing here, though, is that the base level. So in this case, like I said, the base level is R&D. And then base level, it has 0 for sales, 0 for HR. And that's good enough to see like, okay, so that means focus on the can in this right-hand side table. And 0 for both department name. So that means these guys are from R&D. And once we have this, then this basically R&D is 0. So that means when you want to understand Peter's monthly income, for example, compared to CAM, in this case R&D, so like one value increase for the sales means this person is the sales department, or one value increase in the HR compared to R&D, that means this person is HR. So So that's sort of like how you can interpret the categorical variables coefficient. So what that means? Here we get so focus. Let's take a look at department sales. The coefficient of the department sales is $678. So that means when we compare to R&D, then we can expect $670 for sales department employee. Okay, so this coefficient is when you have the categorical variable, it's a little bit tricky compared to the numerical variable, but it's actually not, it turned out it's not that complicated once you understand how that works. So now we understand the slope or coefficient. Let's get to the p-value side of things. Now, so p-value, in order to understand p-value, so what's happening behind the scene is this linear regression model is doing the statistical test on the coefficient. So what statistical test? So basically, like we want to understand, like when we get the coefficient, let's say like $400 or $500 or whatever, if that is something that like we should pay more attention to it. So to test that, then we start with something called null hypothesis, which means the department and the monthly income have nothing to do with it. That's the null hypothesis. And if we can say, if we assume that null hypothesis, and then like we get some like coefficient, like it's still like saying like $400 or something like that, then like basically by doing this like statistical test, we can get this thing called p-value, which is the probability of getting the estimate, in this case, the coefficient, assuming the null hypothesis. So then, for example, sorry, here you go. So let's start with the working years, which we had already. So like null hypothesis, meaning the monthly income, the working years, these are independent. So like there's no effect on each other. And then like we get like $467 as a slope for or coefficient for working years, right? And then now the null hypothesis, oh my gosh, it is Japanese again. Okay. We don't need this information here. So now that we remove, okay, sorry about that. Okay, so coefficient for working years is 0 is a null hypothesis. That means the formula, it can be like 0 multiplied working years. So like no matter how many years, the values, regardless of the value in the working years, there's always monthly income that stays the same, which is $1,227. Then then like you get this p-value. In this case, what is p-value? So let's see here. I'm going to change this predictor variable again to total working years. And then here, the p-value. This is super, super small. It's actually, it said 2.729, but when you look at the most right-hand side of this number, it says E minus 292. That means 0.1 multiply 292. And then you start like a 2729. So like basically you say like 0.0000292 times, and then 2729 and so on. So which means basically essentially this is super close to 0. It's a very, very, very small number. So that means assuming the null hypothesis, which is in this case the total working years and then the monthly income, they are not related. Then we still get this coefficient 467. Is the chance of getting this is that almost like a 0%. So basically, like we're getting some kind of a phenomenon that it's almost impossible. But so that says probably at the total working years, because of value changing total working years, that's why we are seeing the changes in monthly income. In other words, so the monthly income, the values of monthly income can change randomly without any reason, or maybe caused by something else, but not by the total working years. That's the null hypothesis. But we are seeing when the total working years change, and then we are also seeing the monthly income change. And that phenomenon cannot be explained if we accept the null hypothesis. So therefore, we can reject the null hypothesis. This null hypothesis is not really working. So because we're seeing a phenomenon that's almost impossible to happen. So we can use total working years to explain the changes in monthly income. And that's what really the p-value is. So therefore, now we can conclude that like working years and monthly income are correlated. Or more precisely, we can say like we cannot say they are not correlated. So that means like basically like we can say they are most likely correlated. Okay, so now as opposed to that, like let's use other variables. Let's say I'm going to clear the selection. And there's a distance from home. So like how many distance, how many miles, whatever, like you are far from your office where you live. So like if I select it and then run it, and then I get this coefficient. And in this case, coefficient is minus 9.88. Excuse me. So that means the farther you are away from office, then like your monthly income goes down, which is kind of like horrible. But anyway, so but the color is gray here, and it says the gray color is a p-value is greater than 0.05. This is just a threshold. This 0.05 doesn't really mean anything. It's just one of the threshold. You can change this by clicking on the property p-value threshold to be significant. And then typically, we use this number to decide whether this variable is significant in terms of like the effect on the monthly income. But here, the important thing is to understand what this p-value 0.51 means. So again, let's start with the null hypothesis, which is distance, monthly income, they are independent. They don't have any effect on each other. And then we can have the formula or model like this. This time we get a -9 for the coefficient for distance from home. And then the null hypothesis is that like the coefficient for distance is 0. And here is, oops, live coding. It's 0. So monthly income is always stay the same regardless of like what the distance number is. And then like we get this result. And then like when you visualize this data, it actually becomes something like this. So you get something like this. And obviously, like almost when you look at this here, this correlation, the trend line, the correlation looks, it's almost 0. Here we can read it like it's minus 0.01. So it's close to 0. So that is what I was talking about, is when the slope is 0 or correlation is 0. It's basically, it doesn't matter what the distance from home is in terms of like seeing the changes of the monthly income. Oops. I'm going to just make sure this was not going to bother for us. Okay, here. So that means, and then this time we get like p-value as 51%. And then what this 51% is that like basically once in 2 times, right? This is basically 1 in 2 times, we get this kind of change in the monthly income. So like monthly income, again, the value can change. But then like, it seems like that can happen quite often because once in 2 times, right? And then, so that means probably not because of the distance from home value change, probably is something else. So therefore, we can't conclude the monthly income and working as a correlated. Or more precisely, we can't reject the null hypothesis. We start with a null hypothesis, which is like these two values, the variables are independent, or the coefficient is 0. But we can't reject it because it probably, this kind of change in the monthly income can happen randomly or by chance. So therefore, we can't reject. Therefore, we can't conclude they are correlated. So that's really the p-value is. So so this distance from home, that's how we can understand. And then let's go back to the department that we selected before. And if we run this, and then like we get the sales, this is what we saw before. And then here, the human resource, department human resource. And that is also p-value is pretty high, it's like a 0.54, which is again, it's like a one in a two times chance. So probably not because the human resource change and the monthly income change, but here is a p-value 0.01. So therefore, this is probably 0.01 is like 1% chance. So it's very rare. So probably like because this department sales change, therefore like we see the change in monthly income. What the change in department sales, or what the change in department's human resource, again, I want to make sure that is compared to base level. Here, R&D. So that means, though, just a little quick. Here is a scatter plot, and then with the department. What it really is like here is x-axis department, y is monthly income. And then when you see this like a black line, I use a reference line, like you can actually use this reference line to show this line. And then so what we're really seeing is here. So research development and then the sales. So there's a difference here in terms of like average or mean. And then like we're basically testing this difference is significant or not. And according to the linear regression model, that from research development to sales, there's a difference. So therefore, we can conclude there's something going on between these two departments. But human resource, the average is here, and this R&D's average is here. So the difference is, there is some difference, but it turned out it's not significant. And sometimes happen even though when the difference, so the two, so here, so why not significant? So like one is the difference is small. So like there's a difference, but that, very minor difference. So, maybe like just data, again, the values. So maybe that it's not that something that it's important. Another reason is the data is small. So when you look at here, the human resource, the number of the human resource employee, how many? Is like 63 people. And then this happens, tend to happen because of that. There's something called like a central limit theorem or something. But that's another topic. So but not in a nutshell, when you have the small number of the data, then the model can't help you by saying like this has some kind of like a significance. So this happens. So but also it's important to note, just because p-value is high, that doesn't mean that there's no relationship at all. It's just that like maybe like when you have more people in HR, and maybe the p-value can go down. That means we at the end of the day, like we might be able to conclude human resource and R&D have some kind of effect in terms of the monthly income. But anyway, for here, just to simplify, by looking at this chart, the coefficient tab of the linear regression, I think the sales and the R&D's difference is something that like we should pay attention to more than the difference between human resource and R&D. Okay, and the last topic is here. Oh, and also though, one important thing. So another thing is this bar. This is called like a confidence interval. So here, like you see those two metrics: confidence high, confidence low, and so that means this coefficient, it says 677, but that doesn't mean it's just one particular precise value. It's actually ranges starting from 150 to 1,205. And then the confidence interval, in this case, at 95%, is that 95% probability that like this range would increase the true coefficient value. Okay, so that means it can be like 200, it can be 1,000. We are not sure, and so therefore there is that range. This range tends to become shorter when you have more data. So here, when you look at human resource, because we know that human resource, we have only like 65 people, so like there's much less data. Therefore, this confidence interval gets longer, tend to get longer when you have smaller data. And then the range is starting from minus 825 to 1,571. And then the important thing here is it contain zero. So that coefficient can be zero. And then, like I said, so the coefficient zero means that basically the two variables is independent, right? So like regardless of the department resource, human resource, in this case, R&D or human resource, doesn't matter in terms of change in the monthly income. So we can't reject the possibility of that. That's because confidence interval contains zero. So when you're not familiar or not used to p-value, I'd recommend start using confidence interval first. And whenever you see the confidence interval contains a zero, that means coefficient can be zero. That means that basically there might not be relationship between those two variables. Okay, so the last topic is R squared. So R squared is actually pretty important. So here, when you go to the summary view, we already got the coefficient and p-value. Those are two very useful information. But there's another one is called R squared. So let's select the total working years first. And then let's rebuild that model again. And then here we see like 0.59, almost like a 0.60. And that is, this value starts from 0 to 1. 0 is the lowest and 1 is the highest. And then we can say it's more like in a percentage, so like 60%. So what is the 60% about? This R square is some metric to see how good this model compared to the null model, or how good this model fits with the given data, in this case, employee data. And it can be 0 and 1. 1 is the highest. And then so let's take a look at this one scenario. So let's say like two variables are very correlated. In this case, like even like our data is like working years and then monthly income pretty correlated. But let's say like it's kind of like an extreme case, like very close to R squared is very close to 1. The data should be looking kind of like this. Okay, so now let's look at this point now with the black arrow, and then. But by the way, like I want to explain first, is like a mean or like average is a red line. Okay, so average of the Y value, it can be the monthly income. And then the blue line is the model, in this case, a linear regression model, right? And then because this line goes inside, sort of like kind of between points of all the actual data, which is blue circles. Okay, and then, so that means, for example, let's say like when X value is 30, then the predicted or estimated value should be on this blue line. Okay, and then we can say like how much of the difference between the actual value, which is a blue dot, and the predicted value, and also the predicted value and the mean, which is the orange line. Then like we can say like how much of the variability of the data, which is the distance between me and the data, can be explained by this prediction model. Okay, so so the red distance, the red arrow, is the one which is not explained by this model in terms of the variance. But the green part is that is the part that the variance of the monthly income being explained by this model. And then basically the R square is a sort of like a ratio of the green part, and then the distance from the blue dot to the mean. And then so basically the ratio of the green arrow, green length of the entire distance. Then let's take a look at the R square is really bad case. In this case, it crosses zero. Almost like when you draw the prediction line or like a trend line, it's almost going to kind of flat, which is the slope is zero kind of case. And then let's look at the particular data point. And then we do the same thing, like how much of the variability of that data can be explained by this prediction model. And then only the green part is the one this model can explain better than the mean or the average. But the red part cannot explain. Like we don't know like what's happening with those areas. And probably because something else, some other reason, some other variables might be able to explain, but not this particular variable. So R square is really can tell us like how much of the variance of the target variable, in this case monthly income, can be explained by using this predictor variable. In this case, let's say total working years. So that means what we got here is 0.59. So 60% of the variance of the monthly income compared to average can be explained by total working years. So 60% can be explained by total working years, which is pretty good. But then 40% cannot be explained. And then that probably coming from something else. And that is something that we can dig in the next seminar. But so far, we look at that. And then, so the R square is a problem. So R square can be also used because R square can be the measure to evaluate the prediction model, see how the model fits the data. Sort of like we are seeing like how good the model is. But there's there's a note to take here is that if the R square is low, let's say, for example, here is, I'm going to just use a department or something like that. And then when we run it, and R square is 0.004, which is like almost like nothing that this department can explain. So if that is bad, this is really bad. Let's say like when we get like a 0.1 or 2 or something like that, 20%, 10%. So what that means? Well, if we want to understand the relationship among the variables, let's say in this case, monthly income and then any given variable, let's say distance from home, distance from work, or month age or gender, whatever, then we want to focus on like how much of the variance it can explain. And then so it's still, even the low value, like this is 10% or 20%, still it's useful. And if we are not sure if that difference or that little explainability is significant or not, that case we use this p-value. So this p-value is the one we can say, hey, this variable is really having a true effect on the target variable or not. So the R square is really giving you the information about like how much of the variance this variable can explain. But if you are making a prediction, let's say like you build a model and you want to use it to predict the answer, then low R square can be a problem, like because it can explain only 10%. So like that means 90% you can't explain by using this model. Therefore, you can't really depend on this model, right? But here again, like we want to focus on the relationship or precisely the correlation between any given two variables or monthly income and another variable. So therefore, we want to focus on this R square in terms of like as a measure of explainability of the changes in monthly income. Okay, so that's pretty high level basics of the linear regression. but we still have more questions to answer, right? So that is, so we have used a simple linear regression, but the truth is, in this data, there are a lot of other variables, and other variables are correlated to one another. So let's say, for example, age and working years should be correlated to one another. And then one variable change, so age change and working years will change, and working years change, and then that will change age as well. So then, like, we don't know, like, is that because of working years, like, in this company, or is that because this person is getting older, that's why, or we get kind of confused. Which one is really having true effect on the monthly income? So basically, we want to know the independent effect of one given variable, right? So that's something that, like, we haven't been able to figure it out. And also another thing is, this is not necessarily particular to the multiple regression, but also other things that, like, we see the total working years is important here. But is that the same thing in every single department? In this case, the sales department, R&D department, HR department. Is that total working years matters? Maybe HR department might not matter, or R&D department might not matter, but sales might matter. So, like, there might be some kind of like a different effect in different group. And those are the questions that, like, we want to actually look deeper. And also, yeah, I think that contains all the questions. So in the next session, next week, I'm going to get into start throwing more variables, or using something called repeat by to answer these types of questions. Okay, so that's it for today. And if you have any questions, please unmute yourself and then answer your ask your questions. I'm gonna stop sharing my desktop for now. And okay, and there's a chat window as well.